Hi, my name is Nicholas Wiley. This is Material and Energy Balances Homework 2, Part 1. So first up, this diagram right here, we have a P versus V diagram. This is just like for Homework 1 how we had the P versus T diagram, but instead this is going to be using this V down here. And the asterisk is talking about how this is the specific volume, meaning that when we're going to be doing our calculations, this is a volume per mole. So we don't have to consider the mole because it's a part of that factor right there. Now what we're going to be looking at in this, let me turn on my pointer real quick, is we're going to be talking about this critical state right here. And the whole process we're going to be going through is we're going to be using this right here to determine pressure at different temperatures, whether it's above or below or whatever that may be. So when we look at this point right here, we can see, we'll be talking about this in a second, we will see that right here there's no slope. So when we take that derivative, the first derivative, which again will be coming in a second, it's going to equal 0. And also when we take the second derivative, we can see that right here, if we followed this curve, this imaginary curve, this would be concave up, and this would be concave down, meaning that right here at C, at this critical point, that is an inflection point because it switches from concave up to concave down. In addition, I thought I'd explain what the critical point is. Pretty much what comes of this is we are going to be in a fluid state where you cannot tell the difference between the liquid and gaseous phase. It just becomes a supercritical fluid, as you explained, Carlos. When we're at this point right here, I have coffee, let's just pretend this is water and this is closed, we would not see this meniscus, this line right here, because there's no differentiation. The properties become pretty much the exact same, and there's no way of distinguishing between the vapor layer and the liquid layer. So, moving on. Now, to relate this, we have the van der Waals cubic equation of state. And this is what it is right here. The pressure equals the R value times the temperature over V minus B, and B is the accounts for the volume of the particles. So when you have particles of gas in a container, you have 1 mole. You have a certain amount of particles that take up a small amount of space, but they still take up space. So that's what this is accounting for. A is talking about the spontaneous dipole like interactive forces over V squared. So we're just going to be subtracting that as well, and that'll help us determine the pressure. This is pretty much just this was van der Waals' way of accounting for those forces, those extra volume, just to make sure that the ideal gas law, it's just a correction to that pretty much. Now what we're going to be doing is we are going to be deriving this to try and figure out what these A and B constants are, right? So first we start off with this, and I actually don't have a slide, but what I was saying was I added these C's because we are looking at the critical point. And what we're going to do, like I said before, is we're going to take a derivative, a partial derivative of pressure in accordance to the volume, with temperature being the temperature at the critical point, which pretty much makes it a constant value, so we don't have to account for that. That's why it's called partial. And then for the volume, we're also using the critical volume. Now, why does this equal 0? I explained before when we look back at our diagram. Right here, there's no slope. It is flat. So at this point specifically, there is no slope, and the partial derivative equals 0. And with a little bit of algebra, following our algebra rules, we've been doing algebra forever as engineers, this is what we get to. This is our first partial derivative with respect to volume of this equation right here. And then next up we have the second derivative, again using these two, partial derivative, accounting for that our temperature at this point is the critical temperature and the volume is the critical volume. This equals 0 because again, inflection point, concave up to concave down. If you just continued those lines, so an inflection point equals 0. Explain that. And then again, just following our simple rules, 2 goes up there, flip the sign again, bring the 3 up there, add 1. Simple. Now what we can do is that since they both equal 0, we can use both of them together to find the A and B values. Since we have 2 different variables, we have to have 2 different equations. So here we are. Now what I'm going to do is I'm going to flip these. I'm going to follow your steps, Carlos. pretty much just so that it's a lot easier and there's not as many steps. So by flipping it, this is what we get. Now we're going to use both in unison. So just multiplying these together, we'll be able to cancel out, and we end up with this right here. So when you divide out the a's, they disappear. So this is, again, more algebra, boring stuff, and then we end up at b equals 1/3 of the critical volume. Now we want to find a, so we can just take one of our equations and insert b into there. So when we do that, we get VC minus 1/3 VC, so that becomes 2/3. Square that, so it becomes 9/4. Same thing, and then we're going to cross multiply, then we're going to divide, again, more algebra, and we figure out what a is. Now, okay, so also what we could do is that since these are all, we have the TC, we have the VC, we are at the critical point, what we can do is we can say that this is the critical pressure right here. So we plug in our A and B's, and we end up with this right here. Again, more algebra. We end up that our critical pressure equals 3/8 of the critical temperature times R over VC, which is the critical volume. Now what we can do with this, there's something called a compressibility factor, which is Z, which is pretty much just talking about how much a real gas deviates from an ideal gas based off of behavior, volume, all these things, interactions. So again, we have this C right here. If we look at this right here, it's pretty interesting because it looks really close to this right here. So a little bit of reorganizing, and we will end up with our compressibility factor at the critical point is 3/8. Now, I found this really cool when you were talking about this, Carlos. So basically, what this means is that for any van der Waals substance, the compressibility factor is going to be 3/8. You look at all the properties, whether it's the critical pressure, critical volume, mainly just the critical volume, critical temperature. If you plug that in, you're going to get 3/8 pretty close to for every single substance. And I thought that was pretty cool using that using this equation right here.